Hi everybody, this is Mrs. Ewald signing in, and today we're going to talk about stoichiometry, which the cool people call it stoic. So most of the time your teachers are going to refer to it as a stoic problem. So what does stoic really mean? It is a way for us to quantify what those coefficients really mean inside our balanced equation. And so let's first go through the interpretation of a chemical equation. Here's an example. The example given here is N2 plus 3H2 forming 2NH3. Now, that's what most people might see when they look at it. But for me, when I look at it, this is how I refer to it. I see it as more of like a recipe. So it's a recipe that tells me that when there's 1 mole of nitrogen gas reacting with 3 moles of hydrogen gas, it will produce 2 moles of ammonia. So it is really a recipe for what will happen. Just like you have recipes to bake cakes or to make cookies or lasagna, whatever it may be. So what information does this equation provide? Well, first off, it provides to me the particle numbers. So that means those coefficients will also tell me the number of moles. So when there is nothing in front, it's an understood 1. So it would mean 1 mole of nitrogen reacting with 3 moles of hydrogen to make 2 moles of ammonia. Remember what a mole means. A mole is, again, a way to quantify something. It's a quantity. And so if you have a mole of something, 1 mole is equal to 6.02 times 10 to the 23rd particles of something. And we also know that 1 mole is equal to a certain number of grams, right? And that is the molar mass. So it tells us the number of particles. The equation will also then tell us the number of moles based on our coefficient. And what's very interesting is that I can also then find out the mass of my reactants and products by using molar mass, using our handy-dandy periodic table. So let's go through an example, very simple example, of a mole-to-mole calculation. Okay? So remember, a mole is a way of quantifying. It's a quantity. Remember that it means the amount of something, and if we have the information for one part of an equation, we could use a balanced equation to find out more. So notice, we are always going to give you a balanced equation to start. You need a balanced equation. That's why we learned that already. So we're still going to stick with the same example. And the question is, how many moles of ammonia are produced when 0.6 moles of nitrogen reacts with hydrogen? Okay, so now we have a given. I'm going to box that in. So we have 0.60 moles of nitrogen reacting with hydrogen. Okay, so in the balanced equation we have, so how many moles of nitrogen gas do we have? By the way, notice it's nitrogen. So a lot of people think that you need to look at both this and this. Oh, no. That nitrogen is part of ammonia. This nitrogen, we're referring to just nitrogen gas, so N2. How many moles do we have? You look at the coefficient of the balanced equation. That represents then your number of moles. So we have an understood 1 because there's no coefficient in front. How many moles of ammonia are made when you have 1 mole of nitrogen? That would be 2. Okay, so notice it's a way of giving us a recipe. So this relationship can be written as a conversion factor or a mole ratio. So for example, when you compare nitrogen and ammonia, whenever I have 1 mole of nitrogen gas, I can then make 2 moles of ammonia. And this, by the way, is equal to flipping it in the other direction too. So I can also write it as whenever I have 2 moles of ammonia, that is because I had to use 1 mole of nitrogen. So you could flip it either way, and notice now we have these equivalence statements that we used before when we were doing factor labeling. Do you remember that? Yeah, we're going to go back to factor labeling. We have a conversion factor. We're going to be able to cancel out, cross off things, and figure out what our final answer will be. Fun stuff. It's almost as relaxing as balancing equations, actually. So you're going to multiply the whole ratio, the mole ratio, by the given amount. Okay? So whenever we have a start of 1 mole of something to get to how many moles of the other, we're going to use the molar ratio. So just to give you a quick example then, if we wanted to know and actually answer that question, so if we have 0.60 moles of nitrogen, I want to know how many hydrogen is going to be necessary to react with that. So I'm going to go from moles of nitrogen to moles of hydrogen. I'm going to look at my molar ratio, and we know from here that hydrogen is 3, looking at the coefficient, and nitrogen is 1. So it's a 3-to-1 molar ratio. So I would just simply take 0.6 times 3 to find out how many moles of hydrogen I would need in order to make that amount of ammonia. And let me pull up my calculator here. So that would be 0.6 times 3, and that would equal 1.8. Now, moles of hydrogen. You also have to worry about sig figs whenever you do any kind of factor labeling. What do? You just make sure you go from the given. There are 2 sig figs, so I need to have 2 in my answer. Voila! And it makes sense that you're going to need more hydrogen than you do nitrogen. Why? Because it's a 3-to-1 ratio. You need that many more times hydrogen than you do nitrogen. Hopefully you get that concept. Remember, it's very logical. So here again, using the same balanced equation, let's do another type of calculation. So we're going to calculate the number of moles of nitrogen. So when we're given 7.24 moles of ammonia. So I'm going to box that in. That's my given. Always start by writing that out. So we have 7.24 moles of ammonia. And I'm going to go from moles of ammonia. And I want to calculate first, so this would be letter A, my number of moles of nitrogen. So that's going to go on top. Mole to mole. Cancel, cancel. Write in your coefficients. So moles of nitrogen, 1. Moles of ammonia, 2. So now you know that you're going to divide. So you're going to take 7.24 divided by 2, plug that into your calculator. We know we have moles of nitrogen on top, so that will be our unit. Divide it out, and you should get 3.62 moles of nitrogen are going to be required. Does that make sense? Absolutely. Why? Because it's a 1-to-2 ratio. So it should be half the amount of nitrogen needed. For the second half, we want to know the amount of hydrogen. So that would be 7.24 moles of ammonia. Again, starting out with the same given. We're going to write out mole of ammonia on the bottom and mole of hydrogen on top. Hydrogen has 3, ammonia has 2. So I'm going to take 7.24 times 3 divided by 2. Make sure you plug that in correctly. 7.24 times 3, get that, divided by 2, and that is 10.86. How many sig figs should I have? I need to have 3. So that would be 10.9 moles of hydrogen. Box it in, and you're done. So that is your simplest conversion to go from moles of one thing to moles of another. Again, thinking about our recipe, how much do we need of each thing? Moving on now to mass. So, same idea. It's very similar to mole calculations, except we need to convert masses to moles first, right? So if we want to calculate the number of grams of ammonia produced by the reaction of now are given, I'm going to box that in, 5.40 grams of hydrogen with an excess of nitrogen, okay? So we're going to use our balanced equation, same balanced equation that we've been using along the way. So let me just rewrite that so you have it in front of you. N2 plus 3H2 yielding 2NH3. This is going to be our plan of attack. So now we're going to go from grams of hydrogen to moles of hydrogen first. That's the new part. So this here is new. Again, then we're just going to do our molar ratio, go from moles of hydrogen to moles of ammonia. And then again, the new part would be just to have to go back to gram. And that's it. So now we're going to have a multi-step problem. So let's go ahead and write it out. So I'm going to write down my given, 5.40 gram of hydrogen. So I'm going to figure out, so this is the amount of hydrogen that I have in the lab. Okay? And based on my recipe, think about in the end, I want to know the number of grams of ammonia that I'm going to make. So let's say I need to make a certain mass of ammonia for something. This is why I'm calculating it. This is why stoichiometry is so important. So I'm going to put grams of hydrogen on the bottom, and I'm going to go from gram to mole of hydrogen. Now we need our handy dandy periodic table. So make sure you have that, and also make sure you remember your diatomics. That is what will hurt you if you don't remember, because when I have 1 mole of hydrogen, that's H2, it's not 1 gram, it's 2. So that will cancel. Now I'm going to do my simple mole to mole ratio, go from mole of hydrogen to mole of ammonia. Look at my balanced equation. So for every 2 moles of ammonia, I need 3 moles of hydrogen. Cancel, cancel. And now I'm going to do my last step. I'm going to go from moles of ammonia to grams of ammonia. So look on your periodic table and do your total. So when you have nitrogen, that's 14. And then hydrogen, you have 3 of them. So that would be 17 grams per mole. So that means for every 1 mole of ammonia, that will equal 17 grams. Cancel, cancel. That is my unit that I want on top, so I know I'm golden. Now's the thing. Make sure you put this in your calculator correctly. So many people write it out and then they just really bust it up when they try to actually put it in their calculator. Use parentheses. You're going to take 5.4, parentheses, 5.4 times 1, I'm just going to show everything here to be thorough, times 2, and then times 17. Close parentheses, divided by parentheses, 2 times 3. Notice how I did this all laid out in one step. I am minimizing my mathematical error. I'm going to put it all in my calculator in one step, use my parentheses correctly, hit enter, and get my answer. So I get 30.6. How many sig figs should I have? 5.40 is what I have to start, so I should have 3 sig figs in my answer. So the answer will be 30.6 grams of ammonia. Solid. Right? All right. So then another example has you calculate the number of grams of nitrogen and hydrogen that are required to make 100 grams of ammonia. And you want to use the same balanced equation provided. This you're going to try. Do not leave it blank. I do not want to see squiggles. I do not want to see things like, oh, I didn't know how to do it. Go back to this example that I just went through with you. Start off with your new given, solve for the amount of nitrogen and also for the amount of hydrogen. Have fun. All right, this is Mrs. Ewald signing out, saying happy stoichiometry. Peace out.